Hello my dear students, today I am going to discuss about your first unit, that is interference. First of all, we know that we studied optics. In that optics we have classified into two types. One is ray as well as wave. So in the case of ray optics, we have studied about light only, but light travels in a straight line. But in wave optics, here also we studied about light only, but that light will be in the form of wave. Here in the form of particles, in the form of wave. We discussed ray as well as wave. In this wave optics, today the interference will be there. That one also I will discuss one by one. In that interference, the definition of interference due to division of wavefront, Fresnel's biprism, and this Fresnel's biprism experimental setup. So, first of all, interference. What is mean by interference? It is the distribution of this light energy. When the distribution of light energy means the energy will distributed from one ray, two ray, or one or three or four waves or five waves, so on. These are the distribution of this light by using superposition. Using this superposition, what happened? This distributed light will be reunite and form the fringes. This phenomena is called as, these are the fringes, maximum, minimum, bright or dark fringes. The distribution of this light energy will reunite by using this superposition. What will get? Dark or bright fringes. This phenomena is called as our interference. The distribution of light energy will reunite and form the dark as well as bright fringes. This phenomena is called as the interference. So once if it is over, the next thing is interference due to division of wavefront. This thing we studied in the second PUC, that is Young's double slit experiment. See here, consider one narrow ray is formed from, or it is emerging from the source, that is S. One narrow ray is emerging from the source, and consider one slit at having two holes side by side. The ray will come and goes from this hole. What happened? Two rays will be going from that. Means basically a single ray is there. That ray will pass through two different slits. At that time it will produce two different waves. So after some time, by using this superposition, these two rays reunite and form the fringes. Dark as well as bright fringes will be formed. This phenomena is nothing but the interference due to division of wavefronts. Means wavefront division means two slits are there, two holes are there. A single monochromatic light when passes through these two holes or two slits, what happened? This will form two waves will form, because two holes are there, two waves. After some time, those two waves are reunite and form the fringe pattern. This is nothing but interference due to the division of wavefront. And next thing is Fresnel's biprism. Bi means 2. Yes or no? Bi means 2. Here prisoners by prism, consider 2 prisms. It is prism number 1 and another one is prism number 2. Consider 2 prisms. These 2 prisms are joined with the bases. It is also prism number 1 and prism number 2. These 2 prisms are joined with its bases. This setup is nothing but biprism. Prism 1, 2 prisms are there, so it is called as biprism. What this prisoners in this prisoners experiment, what he did, he considered one source. It is a source. Is it? From this source, one ray will go to prism number 1 and another ray will go to prism number 2. Ordinary prism, when you light falls on that ordinary prism, what happened? The deviation will happen. That is, whatever the deviation of light will be, that is the angle of deviation. Angle will, some angle that will deviate. That angle is nothing but angle of deviation, is it? Similarly, here what happened? One light source is taken on light source and passes one ray to prism number 1 and another ray to prism number 2. At that time, what happened? It will produce, means first prism will produce S1 virtual image and second prism will produce S2 virtual image. Is it? S1 virtual image formed from the source S only. S2 virtual image formed from the source S only. But prisms are different. Prism number 1 and prism number 2. But it's both are the same prisms we consider and formed. S1 and S2 are the 2 virtual images. Means these 2 are formed same distances from S. Means S2 S1 is same, S2 S2 is same. Means the wavelength also same. These type of images are called as coherent. Coherent sources. These type of sources are called as a coherent source because the single source produces 2 images with same wavelength. These are called as the coherent sources. So it is the Fresnel's. Next part is the experimental setup of this Fresnel's biprism. In this experimental setup, we have prism, source, as well as we have screen. These and this is the fringe pattern. Fine. First of all, consider this biprism and set up that biprism on the optical bench. Here I wrote here. The biprism is mounted suitably on the optical bench. Once if it is over, the next thing is consider one source. Yes. This source is a linear monochromatic light. Remember here, consider one source. That source must be monochromatic light. Is it? Once if it is over, when you emerge or when the source is obtained here, or source is here, from this source some rays will obtain or emerging. Those emerging rays will falls on this prism. At that time we will get the 2 different, means 2 virtual images. But those 2 virtual images having same frequency, same wavelength and constant phase difference. So those type of sources are called as coherent source because from one source we got 2 virtual images. Those virtual images frequency, wavelength as well as phase differences are constant. So those type of sources are called as coherent sources. After following this or whatever this up, we will get dark as well as bright fringes. The central fringe always bright fringe. On the both side of that central fringe, we will get the alternative dark as well as. Next, determination of wavelength. The wavelength is determined by using the determination of fringe width as well as determination of D. What is D here? This is a separation between S1 and means S1 virtual image to S2 virtual image. We are the next part is determination of wavelength. Wavelength is determined by using the fringe width as well as D. D is the separation between virtual image 1, that is S1, and virtual image 2, that is S2. Whatever separation between S1 and S2, that is nothing but D. Here, first of all, the width of the dark or bright fringe is given that beta is equal to lambda D divided by small d. Here, D is A plus B. What is A plus B? The prism to source, whatever distance is there, that is A, and prism to eyepiece, whatever distance is there, that is B. And lambda, it is the wavelength of the monochromatic light. And D, already I told the separation between S1 and S2. First of all, I will discuss determination of fringe width. To see the dark as well as bright fringes, we will use the micrometer. In that micrometer, I will already told that the central fringe always bright. Is it? Always bright. By using that micrometer, we have to see the dark as well as bright fringes. We used this micrometer. You saw in that cross wire. We have cross wire in that screen. Here, the bright fringes where that coincide at center. At that time, that position is XB. Consider XB is the position of that bright fringe. After that, we have alternative bright as well as dark fringes are there. At nth bright fringe, we have again we see by using this micrometer. It is the nth bright fringe. That position is given by Xn. So, the automatically the beta fringe width of that bright fringe, that is central bright fringe as well as nth bright fringe is given by beta is equal to Xn minus Xb divided by n. It is equation number 2. This is equation number determination of the fringe width. Consider the central bright fringe. By using this micrometer, we see the coincidence in that cross wire plate or screen. We will get the position that is XB, and nth bright fringe again you see the position that is Xn. The beta is equal to Xn minus Xb is equal to divided by n. This is equation number. The second one is determination of D, that is separation between S1 and S2. Consider in our setup we have source as well as prism as well as eyepiece and image formation. So here it is prism, source and eyepiece. As well as this is the image formation. This distance between image formation is D1, and we consider or put one convex lens. So distance between source to convex lens is considered U, this lens is phi. Then the magnification equation, magnification equation is phi divided by u is equal to d1 divided by d. It is equation number 3. Similarly, same setup, that is source as well as we have prism as well as eyepiece, and here also D2 form, that is considered D2. This time here the distance between source or prism and convex lens is very small. This time move that convex lens nearer to eyepiece. At that time the distance between source and this convex lens, it is given by phi, and it is distance between lens and eyepiece is u, and the image formation distance is d2. So equation or linear magnification equation is u divided by v is equal to d2 divided by d. That is equation number 4. We get v by u, that is magnification, is equal to d1 divided by d. Here u by v is equal to d2 divided by d. Multiply equation 3 and 4, that is phi divided by u into u divided by phi is equal to d1 into d2 divided by d into d, that is d square. So u get cancelled, v get cancelled, we get d is equal to root over d1 into d2, means we got small d value, beta value and capital D value. So put these three in equation number 1. What is equation number 1? Beta is equal to lambda d divided by small d. Then we will get lambda is equal to beta into d divided by capital D. This is the equation for wavelength in the case of Fresnel's biprism. So this is all about interference, Fresnel's biprism, as well as its experimental setup. By using that experimental setup, we have to determine the wavelength.